All right, let's get started then. Anybody have any questions about the class, about the past lecture, something you read? And presumably you've gotten through a fair amount of Petrov at this point. There's a lot there. It's a very interesting book. Both of the books, Kleppmann's and Petrov's books, are the kinds of books that you can actually refer back to later because there's a lot of useful information in them.
I noticed that the readings that are assigned don't necessarily align with like the self-assessment.
Oh, are they out of sync now?
Like, I don't
Great.
know, when I was doing them, I was a bit confused.
I'll need to check that. Thanks for pointing that out to me. I didn't think I had changed the order of the readings, but I might have slipped something I shouldn't have. All right, that's good to check. Those kinds of details sometimes, I mean, I just copied it from the previous class. I didn't think it would change. So that's good. Thank you for letting me know, since that's not very productive. Are they behind or ahead? Ahead's worse than behind.
Maybe they're just mixed up.
They're ahead.
They're ahead? Yeah.
Ahead? Okay. So I probably need to move them.
I think that's been like the whole year. Like I was asking questions. I'm like, I don't remember.
Great. Okay. Well, then that's not as useful as it should be. Okay. Well, I wish somebody had mentioned it sooner. I could have fixed it sooner. Sorry about that. And don't forget, we've got the anonymous sheet. If you're afraid of mentioning it because you think that I'm a horrible person or something, very dangerous. I might bite. That's still there, and I still do actually check it. Nobody's used it since I first put it up. And there's like a couple from the beginning, and that's it. Let's see. So today we're going to talk about three-phase commit. We left off talking about two-phase commit. How many of you had already seen two-phase commit protocols? So this is new. Good. It's a pretty common database concept, this idea of using a coordinator with multiple participants in a distributed transaction. That's where distributed systems originated, with the database community. Well, what's today's failure? What are we going to reason from? Here's the interesting weakness in the model that we had last week, which was what happens if the coordinator fails just the worst possible time, after it's collected all of the yes votes, but before it's actually written its log out. So now you're one of the participants, you're like, I'm holding a bunch of resources. I can't let go of those resources until you tell me commit or abort. How long before the coordinator comes back? Who knows? Have you ever had a computer die? Ever had a website that just stopped responding? How long before it starts responding? How long before that computer starts working again? Who knows? Maybe it will never come back. Maybe the coordinator was in a building that just got hit by a typhoon or a fire or a sprinkler going off. Turns out that fires are often less damaging than the sprinklers that put the fire out, because electronics don't do very well. One of the stories they used to tell in my research group here was many years ago, as they were trying to finalize a paper for submission in one of the X600 equipment rooms, there was an overheat condition, the sprinkler went off, and it basically destroyed a bunch of equipment. And the same thing happened again after that was probably 2021 or 2022, where literally they just got like $2.5 million worth of brand new equipment, put it in, and it flooded. And it took another 2 years to get the replacement equipment for the equipment that was destroyed. So I think that they managed to finally get that working like last year. Well, you probably don't want to wait 2 years before you continue your transaction. So how are we going to fix this? What could we possibly do? Anybody peek ahead? Well, as long as the coordinator is working, there's really no issue here. This isn't a common case, it's an uncommon case. That's, again, why I said the failure is the thing that gets hard to reason about because it's the hardest thing for us to even test. Something that happens all of the time, oh, I can build a test for that. It's easy for me to reproduce it. Something that happens once every 3 years is a lot harder to test. And now you have to start thinking about how do I simulate that failure? How do I think about that failure? How am I going to handle that failure? And then we'll get into failure conditions which are impossible to predict, impossible to produce on demand, and we'll realize that at some stage we're going to need to have more tools for this. And one of the reasons that we'll be talking about formal modeling next week, because Finn Hackett will be here on Tuesday and giving a lecture about TLA Plus and Pascal, and that's what he does. He does a lot of work with formal models. And one of the functions or purposes of formal models is to provide a framework or a model in which we can analyze potential failures much faster than we can do in the real world. The DS Labs projects run on top of a discrete event simulator. They literally try to get rid of all of the time-consuming parts and just simulate the interesting events. They look at different orders in which messages could be delivered across the network. They're looking for flaws, for mistakes. They're not doing it in a formal way. They're doing it in a Monte Carlo simulation sort of way. We're sampling a very large search space, trying to see if we can find holes, trying to see if we can find failure cases that we are not handling properly. So those are the kinds of tools you end up using in this field precisely because they allow you to see failures that will only happen typically, rarely, and in production. And that's not the place you want to be fixing bugs. Companies like Amazon and Microsoft and Google and Oracle and IBM and yada, yada, yada pay a lot of money to people who really understand distributed systems and how to debug them for a very important reason. The cost of a failing system is usually measured in millions of dollars per hour. No pressure, right? This is why people have PagerDuty. This is why these systems are so critical. This is why I'm spending a lot of time talking about, thinking about failure, not of the class, but of the systems that we build from what we learn in the class. You have to work hard to fail this class. So, two-phase commit protocol. The coordinator sends the preparer, the participants vote, the coordinator writes the decision to the log, and then broadcasts the decision out, or they unicast it, which is really what happens. Everybody commits or aborts together. We have atomicity now. That's what we wanted. The coordinator's log entry is the last vote, but if the coordinator becomes unavailable, our initial assumption, which was the coordinator doesn't fail, which, of course, in this class, anytime I say something doesn't fail, you should be sitting there in the back of your head going, and what are we going to do when it does? Because it will. That's going to lead us into a situation that I was talking about, where now we're hung, now we're stuck, we can't make forward progress. How are we going to deal with this? So what we're going to do now is we're going to add an extra message. So we're going to fix the problem by making the overhead larger but allowing us to reason about one additional state. So this time the coordinator sends a prepare to everybody. Oh, I should go to the next slide then. This time we send this. We send the prepare to everybody. Everyone votes. Now we send. I'm moving. Right. I'm going to send a message. I need to make sure I go through this more slowly than obviously. I went through these slides this morning too, but I was like trying to make sure there were no major bugs. Right. So the coordinator, before sending the problem, if it crashes, it doesn't matter. Participants didn't do anything. After the prepare and before the decision, the participants have all committed. We are locked and ready to go. They're holding their locks. Some participants know the outcome at that point because we're sending messages out saying, okay, that's fine. Others are still waiting. There is inconsistent knowledge, but we're going to be able to normally that's not an issue. If the coordinator fails in, oh, I see what we're doing now. Okay, so we're setting the partial failure states where some nodes know, some nodes don't know. So it's not just a binary condition either. It's literally, because it's that broadcast word. I don't like that broadcast word. I think I'll take it out for next time. Broadcast implies that everybody's going to get it all at once. But in fact, when these nodes are on different network segments, it doesn't do a broadcast. No one uses IP multicast, which is kind of partial broadcast, and invented by a UBC grad, believe it or not. So now we have this even more awkward situation where you know that the transaction has been committed, but you don't. So you've applied the changes, you haven't applied the changes, now we have an inconsistent state. Remember, we're not allowing anybody outside of our secret circle to see that inconsistent state. But a participant who voted yes at that point doesn't know if the coordinator has failed and is coming back, the coordinator has failed and is not coming back, and it doesn't know what the outcome was. That participant no longer has the option of voting against something because it's already made that commitment. The vote, the commitment is durable. You can't undo it. Now, in the real world, in fact, what it means to undo a commitment at that point is it means you have violated correctness. You have left the system in an inconsistent state. And when things become inconsistent, you end up fixing them. You can build tools that will restore consistency in such a system, but they are outside of the normal framework. In a storage device, if a storage device has a block that can't be read because the underlying medium has failed in some way, the device can actually re-vector any future writes to that block to a different location in the storage medium, and they do that. It's part of the built-in functionality, but they can't read what was there before. So all I can do is give you an empty page. Well, that wasn't what was there before now, so now you have an inconsistent state. We build tools in storage in order to reconstruct that state, because typically we can do that. There are other references to it, so we can do it inferentially. And building those tools is itself very complicated. That's why we don't really want to use those tools on a routine basis. They tend to be complicated, they tend to be buggy, and they tend to be slow. What we've tried to do in building our 2PC protocol here, and in all the protocols that we build, is we're trying to make recovery fast and cheap. Participants, some of them or all of them, are blocked waiting. They're holding locks. Locks are blocking other things from proceeding. So now the other clients who are trying to work against the same database or the same region of the database, if you have fine-grained locks, can no longer make forward progress. 2PC is the simple place. It's the synchronous protocol. It's where we stop. Writing asynchronous code, Building asynchronous systems is much harder to reason about because you've surrendered an understanding of the order in which things happened. Now we're back to building consistent cuts in distributed systems. How do I reason about these things? How do I think about them? That I only see effect if I can also see cause. So I can see an effect, and I can work backwards from that and say, this is what I think caused it. And know that because what I have is a consistent cut, I can reason about, within limits, I can reason about what actually happened or what might have happened. Here, this is the easy way out. This is the easy solution that says everything is linearized. 2PC creates the illusion that everything happened in an exact order. So from outside, no one can see the uncertainty in the inside. We're just fixing it on the inside. We're fixing it in the protocol itself. But it's going to block us under certain circumstances. And we need to fix that. In distributed systems, there is this trade-off. And it's one of the names for this is called the CAP theorem. Correctness, liveness, and partition resistance. And typically what happens is you end up making trade-offs between these three things. You can't have all three. You can only have, at most, two of them. Now, people will, in fact, explore that space and try to find ways of having some flavor of all three of them. So it's not really even a triangle. It's much more an exploration of a space that has strengths and weaknesses. Why is that interesting? Well, because it means there's an infinite number of these systems that you can build, and you often will be called upon to build them in a way that represents the needs of the particular project. If you start building distributed systems, you're going to walk in and you're going to say, well, there's really only Paxos and Raft. And Raft is just an implementation of, well, it's actually an implementation of view-stamped replication, which is itself a simplification of Paxos. Paxos is the general case. But we're starting off with primary backup replication server, which is, as I've mentioned, probably more than what you will need in almost every project you ever work on, unless you end up actually working on a replicated, distributed consensus protocol. Maybe what you really want to do is you want to do practical Byzantine fault tolerance for your project. I don't know. Has anybody even heard of practical Byzantine fault tolerance yet? Does anybody know what Byzantine fault tolerance is?
Just random failures that fix that, like come back to consistent state from failures that you don't know about, or just like it just happened.
So, does anybody know what Byzantine means?
A malicious node that could actually be malicious, or you might not. It might not know that it's malicious. It's just sending false signals, falsified signals.
Any node that is sending incorrect information is Byzantine. It doesn't have to be malicious. It could be malicious. How do I know whether you're just an evil person or you're just mistaken? I can't. And so I will just label it as Byzantine. Not that any of you are evil or mistaken. So I just labeled it as Byzantine. Now, the reason the word Byzantine is used is because it describes an historical place, the Byzantine Empire, which was historically known for the fact that everybody lied. And so for whatever reason, we use the label even now. This isn't Byzantine in that it's not lying. The node isn't misbehaving, the node is dead or out of contact. The network is partitioned. How do we distinguish between a node that has failed and a node that is not on the network? I saw one person's head go. Think about that. Let me know what you figure out. So, in two-phase commit, we are actually making a safety decision, the consistency part of the CAP theorem, rather than an availability, the liveness, or the availability part of the CAP theorem. So we're choosing strong consistency and weak liveness, or non-existent liveness. It's not non-existent because as long as the coordinator continues to work, this system functions correctly. But this is a common kind of situation. We've solved one problem, we've now created a subtler and more difficult problem. Anybody figure out how you tell the difference between a failed node and one that's fallen off the network?
Cannot.
You can't. It was a trick question, wasn't it? You can't tell the difference. And that's going to be really important because what we're going to end up with is an observation that because you can't tell the difference, it means that there's a certain class of problems you simply cannot solve. And that could be a, well, why are we here bothering to talk about this stuff if we can't solve all the problems in the world? And the real answer is, well, we can't solve all the NP-complete problems, or we can, we're not sure yet, and yet we continue to try and approximate solutions to them. And that's the same thing we're going to do here. We're going to change the model that didn't work. So, in two-phase commit, they say, we don't want to corrupt our database, even if it means that the system gets into a stuck state and someone has to come along and unstick it. So, take 2 minutes, talk to the people around you, and say, how are you going to get out of this? You're one of the nodes. Or think about it on your own, too. That's fine.
It'd be a lot messier than usually. We want to limit the documentation probably like just a bunch of coordinator, right? But and this, if anybody else knows that.
It depends on if you're writing. I thought it was. It has to be persistent. Kind of make a new
about like the design solution. So it asks that we also want to include log excerpt for AI. So does that mean like when we utilize AI to like help build our design,
Right.
we want to like
Yeah, just
include
log
a
that.
snippet
Right.
inside in
Right.
the actual design page itself?
Keep it in your. You can keep it in your repo. You don't have to keep it in your design, but put it. If you can put it in your design, that's fine, or keep it in your repo someplace. I just want to be able to see, to understand. Okay, what I want you to do is see if you're using AI. I want you to be honest about it, and I want you to tell me when you see something that surprises you, either because you look at it and you go, "This is complete bullshit," or because you look at it and you say, "I hadn't really thought about it that way." I mean, either of those are the interesting sides of it because they force you to think about something. And it's really easy to get into this habit of AI if people just cut and paste it because they think that it's actually true, but it's not. And I think I'm gonna do a very short talk on that because I actually have been doing a lot of research in this area, and I can explain not only why it's not, but why it's the same exact situation we see in distributed systems.
Right. And just to confirm, it's in like our own CWL repo, like under
Yeah.
the AI folder?
Yep.
Okay, perfect. Thank you so much.
No worries. All right, so what'd you come up with? You were just talking about your stock portfolios and comparing them? Your Bitcoin investments? Internships? Did you come up with anything at all? Did anybody suggest a way of getting out of this? So he was here, and then there.
I mean, we were thinking you could time out, and then after a while check, like ask for the log, since that's the source of truth, and then if you see that it committed, then you would replicate that, or you can ask your peers if they committed, then you could also commit.
Okay, so if the coordinator's down, you won't be able to get its log. So that would be the problem with that. Asking the other participants, and it could be an interesting way of doing it, and I think that's going to help foreshadow some of what we're going to do after this. So that's great. I like that.
Create a new coordinator?
Create a new coordinator, but that doesn't do anything about the current decision, does it?
Just retry it.
Just abort and wait for a new coordinator, maybe?
Abort and wait for someone to fix it. Like, a new Messiah arrives and says, I'm here, you're saved. Okay, that works too. Anybody else? So pretty much everything we do has some sort of limitation related to it. If you ask the other participants, then what happens if nobody knows what actually happened? If you can contact them all and find out they all voted, then okay, yeah, we have a potential recovery there. But what if they aren't available either because it was a network partition? And so one of the other nodes is gone and the coordinator is gone. Because it's not uncommon to leave the coordinator on top of one of the replication services, right? So they could be co-located on the same host, so they're fate shared. So that one, you might be able to get away with it sometimes. You can elect a new coordinator, but how do you agree on that? This itself becomes a distributed coordination problem. And that is actually what's going to motivate a fair amount of what we're going to talk about next week and the week beyond. How do you elect a new coordinator? Which implies, how do you elect the first coordinator? Is the first coordinator just simply appointed? And there are basically two ways that you elect a coordinator in a distributed system. One is by using a property of the potential coordinators.
Is a coordinator also a participant?
Can be.
Okay.
So logically you think of them as separate processes, but the processes can be fate shared. In other words, let's say they're both running on the same actual physical computer. So that's why I say, like the computer gets cut off the network or crashes, and one of the nodes and the coordinator crashes. That's a very common model. But when we conceptualize it, we separate them out because the function is separate, even if the implementation means that they are fate shared in some fashion. It's an excellent question, though. So you could time out and abort, but you don't know what the coordinator did, so you don't know how to handle this particular transaction. So you're left in this indeterminate state. You could time out and commit. Now, it's just the opposite problem of the time out and abort situation. You unrolled everything, you rolled it forward, you don't know what happened. There's no safe unilateral action here. So one thing we could actually do is we can add, this is what I mentioned before prematurely, is we can actually just add one more step to the protocol. See, once you've done this enough times, you're just like, well, of course I'm going to go do this. But getting from point A to point B, for me, well, yeah, three-phase commit. What else are you going to do? But I got to get you there a little bit slower. So in three-phase commit, what we do is we have an extra message that says, can you commit? So that's the vote. And then I send out the pre-commit, which tells everyone that we're proceeding. That's now the marker. This gives us one extra bit of information. And then the coordinator writes the final message, and then it says, now I commit it. This is the interesting point, and this, I think, is going to end up being important to understand how the more sophisticated protocols function, but that is everyone is going to be able to figure out what the final vote was, because the moment you see a pre-commit, you know that everyone voted for the transaction, including the coordinator, even though the coordinator hasn't recorded the commit yet. So now we actually have a way of recovering. Now what you can do is you can say any of these nodes can answer the question of did we commit this transaction or not. If none of the nodes know what the outcome was, they can just simply say it didn't commit because nobody got the pre-commit. And we know that if no one saw the pre-commit, then the coordinator didn't write the commit to the log. Therefore, an abort is safe. If one of them did get the pre-commit, not all of them, just one of them, it only takes one. More than one, it'll be the same analysis. It only takes one. If one of them saw the pre-commit, it knows that the coordinator got all the votes for it and was prepared to commit the transaction, and now it can tell any of the others, or all of the others, yeah, that transaction committed. Now we have an escape. Now we have a way of recovering. Even if we get a new coordinator, the new coordinator can now ask and say, what's the last transaction that you saw? And they can all say, this is the last transaction I saw. I don't know if it was committed or not. I don't know if it was committed or not. Yeah, I saw a pre-commit for that. And now this new coordinator can reconstruct the state. This is why thinking about it from the perspective of the failure is interesting. This has given us the insight we needed. What we need when we get a new coordinator is the information, somehow being able to reconstruct that information that says, I know what the outcome of that transaction was. I mean, this still isn't perfect, though. Maybe some of the participants in the transaction are still down. Maybe the one that knows that the pre-commit was done is unavailable as well. This still requires that I go and check with the other nodes, and only if all of the other nodes say, I'm still uncertain, do I know that that transaction can be aborted safely. So it's not a perfect solution. We're going to have to do better than that, but that is going to increase the complexity of the solution we end up with. But it's better than what we had. It's more recoverable. Go ahead.
I still don't understand what does pre-commit phase, like what's this advantage of it? Because like if you send can commit and then
Can commit is when the coordinator asks each of the participants, can you commit this transaction?
and then I say yes.
You say yes, and then all of the other participants say yes. Now the coordinator sends out the pre-commit message that says, we have voted in favor of this. I'm about to record. And anyone who receives that knows that the decision was to proceed forward or to abort it.
How is it any different from going around all of the participants and asking if they say yes or no?
How is it any different? Because you don't know what the coordinator actually did there. The problem is that there's one voter. If the coordinator's down, you don't know what it decided. It may have decided that okay, so here's the thing. You don't necessarily even know who are the participants in this. And I did kind of hand wave that. You don't necessarily know who the participants are in this. Since you don't know who the participants are, you don't know when you've talked to everyone. Now we can fix that with some configuration magic. We can say there's a configuration server someplace. Now we've introduced another point of failure, but it's like nailing Jell-O to the wall. Okay, well, we'll fix it this way. Well, it's sliding off the wall. Well, here, I'll just stick it up there. I recommend duct tape because duct tape fixes almost everything.
So what happens now if the coordinator receives all the votes and it crashes before the pre-commit? How is it any different than crashing before sending the due commit?
It's in the recovery side now. So if the coordinator doesn't come back within some period of time, you can say, we're going to create a new coordinator. If you are one of the participants and you can get that configuration data, for example, then you can say, I can go and query everybody. I can reconstruct the state of the failed coordinator now. I think that's probably the right way to think about it. What we're doing is saying, what additional information would I need to be able to reconstruct the coordinator state? Now, even in the case where the outcome isn't necessarily clear from what I can determine, I will know enough to say I can make a decision that is correct. That's, I think, one of the what might not be clear here. Let's suppose that all of the participants have agreed to commit. None of them have seen the pre-commit message. A new coordinator shows up and says, "Hi, I don't know what's going on. What's the last thing you saw?" And each of the nodes sends back, "Well, I had this list of transactions that were outstanding. These transactions I had can commit. I had agreed to commit, but I hadn't received a pre-commit message for." So now the coordinator can look at that and say, "Oh, I've heard pre-commits, I've heard can commits from all of the participants in that transaction. I don't know what the original coordinator decided, but that means I can choose to abort it or to commit it, and either of those lead to a consistent solution, even though they're different states. Each of those leads to a consistent state, because that's all I care about. I want consistency." The natural inclination here will probably be to commit it, because I want the newest consistent state. But it's still a correct state, even if you say, "I'm going to roll backwards." This is not a bulletproof solution. It's better, but it's not a bulletproof solution. However, it does provide us with an idea of how we might be able to make this thing more failure resistant. So this allows us to recover from a situation that we couldn't recover from before. So it is, like I said, an approximation of something that is better. And this is not going to be the first time we have to make this kind of a decision. So in the three-phase commit protocol, here, I'll give you a nice little flow chart. So the coordinator says, "can commit." All the participants vote. If everybody votes, it sends a pre-commit. Anyone who sees that now knows that the intent is to roll forward. One extra message, it buys us a little bit of safety at a much higher cost. One extra message to every participant. This is why you often don't see the three-phase commit protocol. By the time you get to this level, you say, this still isn't really solving the entire problem. I'll just go implement Paxos. But this came before Paxos. This came before view stamped replication, which are really the only two, and they're basically the same protocol. The difference between Paxos and view stamped replication is that Paxos actually has a leader election, and view stamped replication, aka Raft, just separated by 20 years, and one was done by a man and the other one was done by a woman, so we ignore the one from the woman, right? That's the way the world works sometimes. And I don't say that because I think it's right. I say it because, in fact, it kind of annoys me. They only really differ in how they choose the coordinator. But what's really interesting is that when we solve Paxos using Lamport's approach, we actually don't need a coordinator. Because the first thing he starts with is the situation where there is no coordinator and you have to choose one. And he reached back into ancient history. That would be 17 years before he submitted the Paxos paper. He reached back into ancient history and he used a technique he had already taught people. And we're going to get there. But that's the reason I say you won't see a lot of three-phase commit. People do implement it occasionally, but it's not common because it's a lot more complicated, it's more expensive, and by that time they're like, but we know we have better tools now. But I want you to understand three-phase commit because it's important to showing you the escape from the two-phase commit problem. How are we going to get out from this? And distributed systems, you may actually start feeling like you're Houdini, who was a famous escape artist who actually died because he couldn't escape from his own straitjacket inside of a tank of water because he had an appendicitis in the water. See, no matter how many failures you think you've envisioned, you probably have never envisioned dying in a tank of water in a straitjacket because you had an appendicitis. Or you've read about Houdini, in which case you might have. I don't know. It constantly amazes me the way that the universe will throw failures you've never even envisioned at you. And this is relatively old, 1981. View stamped replication is, I think, 1987. So 6 years later, we get a more robust solution. And then 1991, not published until 98, because no one understood it, was Paxos. So if the coordinator dies after the pre-commit, then the participants are all in the pre-committed state. They know that everyone voted yes, it's safe to commit without the coordinator. One of the participants can actually now become the new coordinator. This is kind of like, okay, great, I'm going to volunteer because I know what happened there. I can recover from this successfully. If the coordinator dies before the pre-commit, we haven't told anybody. If some participants here might have voted yes, but no one is pre-committed, it's safe to abort because no one's promised to commit. No one has made that irrevocable decision. They've said, I've got everything ready, but I haven't applied anything. So that gives us a little bit more information. But there are a lot of assumptions that go with three-phase commit. One is messages arrive within some known time bound. That one's going to bite us. Timeouts mean dead, not slow. That's kind of the same as the first one, just from a slightly different perspective. And the processes can distinguish crashes from delays. In other words, I know if you're dead versus I know if you're just like taking your time to answer me. Yeah, there's a heartbeat there. You're not dead yet. What happens when you don't have synchrony? The coordinator could send a pre-commit to one of them and crash. The network partition, yes, that's why they use the word broadcast here. The broadcast implies that everybody's going to receive the pre-commit. That's why you do it. But in the real world, that isn't. This is my problem. I snap to the real world. Well, of course you're not going to do it that way. No one sends actual broadcast network messages across the internet. They send directed unicast messages. So we solve one problem, we create another one. Hey, I'm going to do this across the internet as opposed to on some LAN segment. On a LAN segment, you can do a broadcast. Everybody's going to see that broadcast, hopefully. And so we don't have to assume that. But when we start looking at what the real world does, we have to bring ourselves back down and go, okay, well, this will help, but it doesn't solve the more general case. Without synchrony, we end up with commits on one and not commits on the other, and now we have inconsistency. And so now we're going to have to go off and build those tools that restore consistency to our beautiful, glorious distributed system. Network partitions break three-phase commit precisely because they mean we can't tell the difference between dead versus slow. So you can't distinguish a crash node from a slower partition node. You can't distinguish between a node that will never respond. Sorry, this computer has been obliterated and will never actually appear on the network ever again. Versus, yeah, well, it's got a bad disk drive, so we've got to restore that, reinstall the operating system, restore the backup, and next Tuesday it will be up. You can't tell them apart. So regardless of which of those you guess happened, there's always going to be some failure case. And that is really the fundamental problem. And unless we have a synchronous network, 3PC doesn't actually prevent inconsistency from arising. So it's a great solution, except it doesn't work. What is this one? Okay. All right, so this led us in 1985. It was actually presented at a workshop, I think, in 1983. So this gives you kind of a time frame for all this. 3PC is 81. FLP, Fisher presented this at a workshop in 83, and 2 years later, he and Lynch and Patterson actually published the paper that says, and this is a very mathy paper, in an asynchronous system where even one process can crash, there is no protocol that guarantees consensus will be reached. And what that means is, I'm sorry, you can't actually solve this problem in this general case. 3PC solves it if you remove the asynchronous. But it doesn't solve it if you actually work with an asynchronous network. So, well, one solution here is just don't use asynchronous networks. We'll just make everything synchronous and life is good. Why do we use asynchrony in the first place? Because we like really complicated systems and it's much harder to reason about?
And in a way to guarantee liveness blocking, like you don't want slow systems.
Wow, I was thinking about something much higher level, but okay. Yeah. Why do we do any of the crazy things we do in systems? Why did we add multi-threadedness to systems?
To make things faster?
Right. The way I usually describe this is that performance is the altar on which we sacrifice systems. In other words, we do crazy things to our systems in order to make them run faster. We don't introduce complexity because we like complexity, although there's a certain amount of fun to complexity. We introduce complexity because we want them to run faster, because people don't like to wait because everyone is impatient. When you ask ChatGPT a question and it hasn't answered in 3 seconds, you lost interest. You're off on TikTok now. And then you go back and you look and you're like, what did I ask? So this is actually a really interesting paper, and I have, in all of the time I've taught this, and I've taught this, been teaching variants of distributed systems for 8 years now, here in person and online at Georgia Tech. And one time, I had a student who forced me to go through every piece of this proof because it is a formal mathematical proof. And the hard part of this proof is that it is a proof by contradiction, which means that one of the lemmas actually demonstrates how you construct a model that always provides a counterexample. And essentially, it's the delayed network that is really the heart of that. That's the reason the counterexample is important to understand. It took me a while to go through the math very carefully. I mean, I was a math undergrad major, so I can do it. It's just in computer science, when you see the formal proofs in a CS paper, almost anybody in systems, their eyes glaze over and they just kind of move on to the next section. You're laughing. Are you a math person? You love reading the proofs? Or are you one of the people who your eyes just glaze over and you go, oh, I don't know, that's really too hard, and I go on? Yeah. The reason that particular lemma is important is because it taught us why this didn't work. And that was, it's the unboundedness of the messages. So the actual solution to this is to just simply say, I'm only going to wait for so long to get a response. And after that, I'm just going to declare that it's dead. And I will ignore any responses that come in after that point. And by doing that, I've created a bounded failure condition, whereas before I had an unbounded slowness condition that I couldn't reason about. That's the way we pragmatically solve it. It doesn't invalidate the proof. The proof was the problem you're trying to solve isn't solvable. And the reason that was important is because people were trying to solve it. And what they were finding is this system we just built doesn't work right. It works most of the time, but then we put it out in the real world and it ends up failing. So, this means that you can actually achieve safety or you can actually achieve liveness, but together you can't actually build a system that has both of those guarantees. I don't think anybody, I think I asked this question before. Anybody take 421? So 421 is theory of computation. And there are these things that we actually, all of your computers basically are based upon this model of what's called the Turing machine. There's actually a programming language that is essentially a language that you can build Turing machines in, because it's literally telling you it's a tape drive with a, you can read from the tape position, you can write from the tape position, you can move forward, you can move backwards, and you can make decisions based on what was on that cell of the tape. And the name of that language is, and I wish, well, I'm not making this up, it's called brainfuck. And people actually do write code in that. In fact, if you probably ask ChatGPT, it can write you a nice hello world. The interesting insight from that model was that it's surprisingly general. It describes exactly, how many of you have heard of P versus NP? Right, okay, well this is same field. The concept of polynomial time bounds versus non-polynomial time bounds refer to the implementation of this using Turing's model. And Turing's model basically said you can actually build a universal Turing machine. In other words, a Turing machine that you can give another Turing machine description to, and it can run it. And if you think about it, what you do is you type things in one language which get converted to something else which then gets run by a processor. We literally use this model all of the time. The observation that Turing made was there is no solution to the question of does this Turing machine, for any arbitrary Turing machine, halt? It is exactly the same scenario. The question here is, does this message ever get delivered is the same as, does this program halt? The only way to answer that is to run it. And the only answer you can get is yes. Because if the answer is no, you'll never get an answer. And this is a really simple idea that now shows up in distributed systems as well. And this was actually published in 1985 in the Journal of the ACM. This isn't engineering. You can't out-engineer this because literally this is just a limitation of the model. Change the model. That's what we're going to do. We're going to change the model. Now the reason, I had thought this was in the next lecture, not this lecture. The reason I find this interesting is because recently I have been doing work on AI, on large language models, on any predictive token-based model. And I actually have a proof that mirrors the same proof that shows that given the interface, and this is an interface issue, it's not I'm not making a judgment call here, it's literally just a restriction of the interface. Given the interface that we have to existing predictive token models, you literally cannot tell if they are telling the truth. And no matter what you do, you can put layers on top of them, you can't reproduce whether or not they thought they were telling the truth. Now that's not whether they were being truthful, it's whether or not they thought they were being truthful. And you know what the best part is? The hardware actually knows. The hardware actually collects enough information that you can detect when the large language model is making things up. But it's no more cognizant of that than you are of what parts of your brain are lighting up when you're sitting here in class or when you're watching a TikTok video or you're listening to music or you're playing games. So it's fun to me because this directly ties here, and the concept, the idea of showing that something cannot be achieved within a given model is powerful. Not because it says, abandon all hope, but it says, look at what you had to do in order to prove that, because that's going to be the weak spot. That's going to be the thing you need to change in order to create an alternate path. How do you escape that? Why is consensus impossible in this case? FLP says, the proof constructs an adversarial execution where you start in a state where the decision could go either way. Now this is kind of like, remember I was talking about lattices? So we know that there is a point beyond which the system no longer has any variability in it. And there's a point before that where the system has variability in it. And somewhere, regardless of which path we take between those two steps, is something that happens that causes the potential future space to collapse. So I have two possible outcomes, I have two possible outcomes, I have two possible outcomes, I have one possible outcome. So that decision. And then the way that you build the counterexample is you just push that decision out further. You just put some more stuff in between. And you can say, no matter what you do, you can always push that deciding message out a little bit further. And you think about it, okay, I can buy that. So, instead of getting from point A to point B, you decide to go to point C first, and then to point B. And then it's not taking long enough. I'm going to go to point D, and then C, and then to point B. And you just iterate. You just keep doing that. I was like, okay. And this is why we bound it. We basically say, look, you can only go through 5 extra neighborhoods on the way to get there. And that limits the ability of the model. It limits its generality, and it allows us to escape the impossibility. And that ties back to my comment several times. You can't tell if a message is delayed or if the sender has crashed. They're just indistinguishable. Because delayed in an asynchronous system is not bounded. We put a bound on it, now we can at least reason about it. And that's what we're going to do in distributed systems. We cannot solve the general problem. We are going to solve limited instances of the general problem. FLP doesn't say that consensus is impossible. It just simply says that it's impossible given this model. Restrict the model, now you can reason about it. It also doesn't say distributed systems are hopeless. All it says is we can't provide guarantees in the arbitrary case. So don't try to solve the arbitrary problem. FLP says no protocol can guarantee termination in all runs. There's always at least one bad run where things stall, and you either accept probabilistic guarantees or you weaken your assumptions. You put limits on the models that you will support, and that's the approach that we're generally going to take. You can take sometimes it fails, and that's okay. I'll just simply have pager duty that day, and someone will have to go and kick the machine and cause it to restart. But that's not the model that we were looking for. Paxos and Raft and view stemmed replication and any of the other variations of this. Let's see, there's Paxos made simple, Paxos made moderately complex, fast Paxos, flexible Paxos. There's a lot of Paxoses. And then there's Raft and view stemmed replication. They all use the same kind of protocol like we see in 2PC. How they use it, the precise details of that protocol vary based on 2 axes. One, which is how do we agree on the decision or outcome, and 2, how do we restore consistency? And the variation is much greater in the how do we recover from failure case. That's where the interesting part of building a distributed system becomes. How am I going to get back to consistent state? Because right now, I'm not in a consistent state. Things are going bad. Life is terrible. How do I get back to happy space? I mean, assuming that consistency is happiness. Maybe you're chaotic evil, in which case then that wouldn't be happy space for you. It would be a sad space. That's Byzantine. We'll get there. So the interesting problem here is that, so we kept adding things to this, right? That was our solution. We started on a single node, we added a log, then we needed nodes to agree, so we added a coordinator, then we have coordinator crashes, so we have a backup coordinator, and then backup crashes, and we add another backup. And so no matter how many times we put another turtle in here, we don't actually make the problem go away. Turtles all the way down. And if you've never read the Discworld series, you really should. It's pretty funny. Terry Pratchett has a remarkably wicked sense of humor. Anybody ever read or seen anything by Douglas Adams? He's got a remarkably wicked sense of humor as well. What is 6 times 9? 42. That's the joke. You will hear people in our field use the number 42 as if it were magic. When Claude is making up seeds for random number generators, and that is ChatGPT does this too. They like to use 42, and that's because it's a reference to Douglas Adams. Now, in fact, 6 times 9 does turn out to be 42 in base 13, but that was not Douglas Adams' intent. I heard an interview with him one time where he said that he actually hadn't planned on that. It was actually because there was a bug in the machine. Because the machine was the Earth, and the Earth was built by mice to run an experiment. Did I not say, very interesting, a lot of fun to read because it really sort of goes, wow, that's a different way of looking at the world. But you're in distributed systems, so you're already in the different way of looking at the world approach. So now the question becomes, what happens if we actually make the coordinator replicated? Can we solve this problem? See, did you notice that in two-phase commit, everyone has to agree on the outcome? Could we build a system where we didn't need everyone to agree on the outcome to solve the coordination problem? Because the real problem with this approach is that if any of the nodes fail partway through, we have to abort the transaction. So we have a scaling issue. 5 nodes on a local area network, fine, not a big problem. Let's do 50 nodes where some of them are in geosynchronous orbit around the planet, some of them are in different data centers on different continents, and 2 of them are on Mars. What? Why would you put something on Mars? Well, because that way we can make sure that Elon Musk survives the apocalypse. Isn't that why he wants to go to Mars? Does anybody know what the propagation delay is between here and Mars for a network packet?
It's variable. Depends on the distance between Earth and Mars.
What, you mean Earth and Mars don't stay the same distance?
Both of them are orbiting around.
At different rates, yes, I know. Do you know what the range is? It's between like 20 minutes and 2.5 hours. So when you start thinking about 2.5 hour propagation delays, it changes your thinking, which I find interesting because it's not really orders of magnitude different than when you think about same rack in a data center versus rack in data center to moon. It's kind of the same sort of scale, a couple orders of magnitude difference, and you're like, okay. But it's easier, I find, usually for people to think about the difference between 20 minutes and 2.5 hours than it is between 80 nanoseconds and a second. I think it's a second. I think it's a second to the moon. I used to know these things. Why would anybody put a data center on the moon? First time I taught this class, I actually used the lunar data center as an example. And while I was teaching the class, some startup company was funded for $5 million to design a lunar data center. And I laughed. I was like, this is great. I love it when the real world actually decides to tag along. So we could replicate things. So if we use 3 nodes, and 3 is often the magic number in these things, surprisingly enough, we could have one of them crash, and 2 of them could continue. And we could continue to reason about this. So to do that, though, we'd need the 3 nodes to agree on the coordinator. So we're back to the coordination problem again. What? It's just the same. We're just looking at a different turtle. So how are we going to solve that? Well, maybe we could be more creative than we did with two-phase commit. Because here, it's a more restricted problem. See, in the two-phase commit, your database and my database aren't necessarily identical or not supposed to be identical. But in the case of the coordinator, we're solving a smaller problem, which is we want a replica, an identical copy. So now it's going to open up the space for us. And that's what's going to lead us into the more sophisticated protocols, into Paxos, view stamp replication, Paxos, and all variants there. So what modern systems actually do, they accept two-phase commit. That's actually still very common. They avoid synchronous coordination, but they accept the fact that this now gives weaker guarantees, that there are going to be times when you have transactions, you just don't know what their outcome was. Or the other solution is you just simply say, hey, I like complexity. I'm going to go build something that almost no one will understand. And if you think I'm joking, I can tell you I've had people finish this class and go, yeah, I did an interview and I was able to explain Paxos to them and they were amazed and hired me. Now they won't do that because, of course, ChatGPT probably knows Paxos better than you do. Except ChatGPT will then try to build a Paxos-based, any of them, Claude. We'll use Claude because Claude is the best programming tool at the moment, at least for the next 30 minutes. And Claude will forget what it wrote tomorrow, so you won't forget. And you'll be able to provide that extra chunk of memory. And that's actually what really happens. These systems get complicated very fast, and they don't work well with the scaling limits of existing AI. So your job is to, of course, build distributed systems so we can then extend their memory so you won't have a job. Perfect. You can just play video games or sit on the beach or what is it? Gregory Hinton suggests that people learn to be plumbers. Real-world example of a failure from 2018. This was where the lightning storm was in Texas and cooling failed, the servers overheated, and the hardware was physically damaged. They had asynchronous georeplication, which meant that they lost data that hadn't been written out. So they either had to wait and recover the data from actual physical backups that were in the original data center, or fail over to the replicas that weren't up to date. So they chose performance over correctness. These kinds of trade-offs are what you end up constantly deciding when you build these systems. It was like I've mentioned in eventually consistent systems. Essentially, that's what we do with eventually consistent systems. We go, most of the time, it just doesn't matter. And so eventually, in the fullness of time, out in infinity, when I'll be dead and it won't matter, if it doesn't work, somebody can open a bug report, I will fix it. Eventually it will be consistent. And the joke in the industry is literally eventually consistent means never consistent. But it's close. Google Spanner uses a completely different approach, which was they used two-phase commit for distributed transactions. They cheat. They use a global clock. The coordinator is replicated using Paxos, and they use this thing called true time, which literally used GPS-based clocks, which at the time, I think when they did this, they said they cost $500,000 each. Now you can go buy the things that are like under 5,000. And people put them in data centers. Your phone and your computer are using sources of time that are highly accurate. Your phone can actually use GPS. If your computer has GPS capabilities in it, it can also figure out what time it is. Within limits, it is still bounded by special relativity. You cannot escape Einstein, not yet. So the trade-offs here was that they actually had higher latency. They did require the special hardware with the atomic clocks and the GPS, but it was globally consistent and not blocking under the Paxos assumption. So remember I talked about the fact that you can solve this problem if you have a global clock? They implemented a global clock system. And the funniest part is when you read the global clock system, they know what the variation in the clock is. They've measured it, and so they just delay packets by that amount of time. And you're like, what? But it does actually work. They're just simulating the network delay, so they know that if they haven't received it in that time period, they're not going to. It's like, okay, there's a lot of math in that one too. So the limits of coordination here depend on exactly what you're looking at. So two-phase commit is blocking this uncertain state. We don't know what to do because there's a coordinator that's failed. Three-phase commit helps with that, but doesn't work in asynchronous environments. FLP basically says, yeah, the asynchronous case, sorry, you can't actually solve that generally. You're going to have to make some compromises here. So we compromise. And we can't keep putting layers here because that doesn't solve the problem either. And so in the end, the solution that we're going to now look at is, can we replicate the coordinator? And this is what modern distributed systems often end up being. They end up being different kinds of replication for different pieces of the system in order to give different guarantees. The reason that next Tuesday's lecture is in fact useful is because TLA, I think I mentioned TLA is a formal verification language that was created by Leslie Lamport. Never heard that name before, have we? I mean, he gave us LaTeX, he gave us bakery tickets, he gave us Paxos, he gave us vector clocks, he gave us lots of things. He's been working in asynchronous distributed systems, concurrent systems and distributed systems. He's been working in this space for a long time. And I don't think he's retired yet. Last time I checked, he was still actively working at Microsoft in research, and he's like, got to be 77 now. And if a 77-year-old can be president of the United States, then clearly, you can be a 77-year-old CS researcher. So there you go. We've gone from single node failure to multi-node failure to coordinator failure, and we keep seeing the same patterns over and over again. We like stacking turtles. The turtles might not like it, but we do. We just keep using the same tools. Now, in design project 1, the view server is your coordinator. And so that's one of your failure cases that you have to reason about. Nothing interesting here, just the usual logistics stuff. Any questions?
So it was about slide 13, it was a while ago, but...
Slide 13, boy. Yeah, that was a couple ago. 13.
Yeah, so just a question about the case where the coordinator dies before the pre-commit. So what if the coordinator decides to commit and writes to the log and then dies before sending the pre-commit? Isn't there still a gap in that information?
He can't do that, right? He actually has to write the log after he sends the pre-commit.
Okay.
You have to sequence that correctly. But that is a really good question because it actually points to the fact that ordering in these systems turns out to be really important. that a lot of times we assume linearity along at least a portion of our solution space, and knowing the order that works and the order that doesn't work is really useful, because if you do it wrong, your system's not going to work right. This is one of the reasons why modeling becomes really useful. If you put that in the wrong order in your TLA plus specification, the model checker would have actually come back and said, sorry, you fail. Because that's what model checkers do. They actually give you a set of states that you go through that lead to a contradiction, that lead to a violation of your invariants. Invariants are just your promises, the things that you say will never happen. Like, I will never give a message, I'll never give a value from the database out to a client unless that value is persistent. Now, I'm being very hand-wavy about that, but Finn will be talking about how you actually express these things. I'm excited because I've talked about TLA+, but I've never been in a position to be able to hand it to people, because honestly, it's a interesting tool to wrap your head around. But AI have actually been trained in it, and they can write better TLA+ specifications than you can. And so you can use this now as a segue, a way to use these kinds of tools more effectively that wasn't possible before. And who knows, maybe one day you'll be like, oh, TLA+ is so cool, I'm going to learn it on my own. Or more likely what will happen is you'll be like, I'll go read its spec and kind of smile and nod, and then I'll ask ChatGPT if Claude's TLA+ is correct. Or you'll go ask Finn. Hey, he's a PhD candidate. He needs work to do. So, great question. Others?
Do you have any, I guess, like guidance for how to approach the design submission that we have?
Did you look at the samples? There are 6 samples on Canvas.
I'll look.
I mean, part of the exercise here is tickling those parts of the brain that will lead you to gain that exact set of skills. How do I write a good design? And part of the reason that I'm going to make you implement someone else's design is because then you'll actually get an example of either a good design or not good design, and the experience to help you understand what matters and what doesn't. Does that make sense? But the 6 examples actually came from a previous iteration of this class on the same design project, and were picked by, not me, but by the TAs, who were not necessarily distributed systems experts. So they looked at them and they said, this helped me a lot in understanding things. And if you still have questions, let's see, today's Thursday, there's TA office hours tomorrow, I think. There might be some today. There's only one day in the week that there's no office hours. Because I moved mine like 3 times as the TAs were picking slots, so I would be not overlapping.
So for the design project 1, thing due next Tuesday, we just have to do like a PDF for like just a design, right? We don't have to...
You don't have to implement it.
Okay, yeah.
You have the code there if you want to implement it because you're more comfortable. And I've had people say this. I'm much more comfortable writing code than I am writing a design. It's like, that's fine. Right, and if you just want to write it as a markdown file and then turn it into a PDF, I don't know what you've got on your machine there, but Pandoc turns markdown into PDFs. Interestingly enough, it does it by turning it into a LaTeX file and then turning it into a PDF. I have a VS Code plugin that I just pull up the command palette and say save the PDF, or save the markdown as a PDF. That works fine too. Super easy. So the idea was the PDF is easy for people to look at because everybody's going to have a PDF reader. But if you want to do it in Markdown or you want to do it in Tech or LaTeX or something, that's fine too. Or if you want to do it in Word, although I'll have no respect for you because this is computer science and we don't respect people who use Word.
Yeah, so just to clarify, it's just a design plan, right? No.
Correct. I mean, you don't have to write any code at all. The code that you get to write will be after, so then next you're going to be reviewing other people's designs, and then the code you write will be one of the other designs you reviewed. You're going to actually then try to implement that. And the goal isn't to make a working system. The goal is to say, what did I miss in my design review? Because I don't know how else to show you how to build a good design, other than trying to take a not so good design and implement it. Does that make sense? Yeah. I mean, I'm open to suggestions. If you discover some magic way to make building good designs easier to teach, I'll buy you a beer. Assuming you're 19, right? I kind of figure most people in this class are. Cool. I am going to stop recording so people don't have to listen to me banter on.